In this video, I'm going to explain the derivation of a general heat conduction equation in Cartesian coordinates, or also known as rectangular coordinates. For the derivation, let us consider a cubical object or rectangular object which fits in x, y, z coordinates. Right? In x, y, z coordinates. The element has a length delta x, a width delta y, and height delta z. And in the x direction, the heat that we are going to supply is a qx. In y direction, the heat supplied is qy. In z direction, the heat supplied is qz. The heat flows through the element for some thickness delta x in x direction, delta y in y direction, delta z in z direction, and comes out. Suppose in x direction, the heat that is coming out is a qx plus delta x. For the convenience, we have that notation like qx is the heat that is applied, which flows through a thickness delta x. So there will be some change in heat input delta x, and that change, with that change, the heat that is coming out in x direction is a qx plus delta x. In the similar way, qy is the heat supplied in y direction into the element, which flows through a thickness delta y and comes out as a qy plus delta y. In z direction, qz is the heat supplied, which flows through a thickness delta z and comes out as the heat q z plus delta z. These are all rate of heats, remember. These are all rate of heats that supplied and coming out of the element after flowing through their respective thickness. And this element have some properties like the density rho, specific heat c, thermal conductivity k. As the heat is supplied to the body, there will be some internal heat generation taking place inside the body, and that internal heat generation is indicated with capital G for throughout the element, and the volume of the element is indicated with capital V, which is the product of length, width, and height. Now let's start the derivation. The energy balance equation for this element after a small time interval delta t can be written as the change in energy. The rate of change of energy is the difference between the input heat and output heat. Right? The change in energy is equal to the rate of heat that is supplied to the element and the rate of heat that is coming out of the element. The difference between these two will give us the energy change. Heat is a form of energy. That form energy change after a time interval delta t can be obtained like this. But according to first law of thermodynamics, the heat supplied to a body or the energy given to a body, a part of it is utilized to generate some internal work, and that internal work here is treated as a internal heat that is generated inside the body. So the total change of the element of the body is the difference between the input and output heats plus the rate of change of, also the rate of heat generated inside the element. Right? Now we know all these things. Now substitute them. The heat that is given as input in x, y, z directions qx, qy, qz, their summation minus the rate of heat that is conducted at or coming out of the element at x plus delta x, y plus delta y, z plus delta z as a qx plus delta x, qy plus delta y, qz plus delta z, plus the total internal heat generation capital G is equal to the change of energy, the rate of change of energy, as we said, rate of so this will be divided by delta t. Remember, here every time q is taken as rate directly, but here the rate is indicated separately by dividing the delta E with the delta T. So let us say this is a equation 1. Now consider this delta E, the change of energy of the element. We know delta E is equal to output energy minus input energy, the difference between these two, or simply saying from Joule's law, the change in energy is equal to mc delta T, right? From Joule's law, from that we can write delta E is equal to mc delta T. Delta T is temperature difference. Remember, every time in my videos, capital T represents the temperature, small t represents time. Capital T for temperature, small t for time. mc delta T, the delta T is the output temperature divided by input temperature, right? mc delta T is equal to mc into T after flowing through the element for the time T plus delta T minus temperature before entering into the element at a time T. So delta T is equal to mc T at a time T plus delta T minus T at a time T. We know the density rho equal to mass by volume, from which mass can be written as density into volume. Now substitute this mass in this. So delta E element will become mass is equal to rho into V. V is volume, and that volume is delta X into delta Y into delta Z into C is C, the temperature difference. This will be change in energy of the element. Now the internal heat generation of the element capital G, that can be written as a small g into volume. Small g is at any point whatever the heat that is generated at any point in the element, whatever the heat generated is small g, and it is multiplied with the volume of the element. We obtain the total internal heat generation. So small g element equal to capital G element equal to small g into volume. The volume is delta X into delta Y into delta Z. Now substitute these two into equation 1, and we have obtained an equation like this, right? Use no dashes are there. Remember, they are plain qx plus qy plus qz minus qx plus delta x, qy plus delta y, qz plus delta z plus g into capital delta x into delta y into delta z equal to rho into c into delta x into delta y into delta z into temperature difference T at a time T plus delta T minus T at a time T divided by delta T. Now let's rearrange this equation and divide the entire equation with delta x, delta y, delta z. The rearrangement is in such a way that all x terms as a set, all y terms as a set, all z as a set. So here you can see all x terms as a set, all y terms as a set, all z terms as a set, and the equation is divided with the volume delta x into delta y into delta z, so that you know delta x, delta y, delta z, and here they get cancelled. Now we know the areas of the sides. Suppose consider this element again. In this element, in the x direction, this is the face exposed in x direction. In the x direction, the surface area, cross-sectional area in the x direction is a length into width, that is delta y into delta z. So area in x direction, ax equal to delta y into delta z. If it is y direction, this is the face that is exposed in y direction, or the face behind this, whose area is a length into width. The length is delta x. So length is delta x into width is now this here delta z. So area in y direction, ay equal to delta x into delta z. In z direction, this is the face that is exposed, and that face area is length, that is this delta x into width, all this is delta y. So a z equal to delta x into delta z, so delta y. The same as indicated here. Ax equal to delta y into delta z, ay equal to delta x into delta z, az equal to delta x into delta y. Now consider the first term without minus. Right? Let us consider the first term. As we know, the delta x, delta y, delta z, delta t are very small as that tend to 0, almost equal to 0, or they may tend to reach 0. By considering that case and taking the first term and apply the limit delta x tends to 0, 1 by delta y into delta z into q of x plus delta x minus q of x divided by delta x. As delta x tends to 0, the difference between these two temperatures is very small as almost negligible. And for those small quantities, we indicate the difference with a d differentiation. Now this term has to be written as dq by dx, but the heat change is not only taking place in x direction, it is also taking place in y and z direction. So the partial differentiation dou qx by dou x is written, as the change in heat is not only in x direction alone, it is also taking place in y and z direction. So dou qx by dou x is the change when delta x tends to 0. So the equation will become 1 by delta y into delta z into q of dou qx divided by dou x. From Fourier's law, we already discussed in our last video, q is equal to minus ka dt by dx. Substitute that q in place of qx. We have minus ka dt by dx. The dt by dx is replaced with dou t by dou x in x direction. Area is delta y into delta z. As it is in x direction, we need to use ax, a suffix x, and that is delta y into delta z we have already. Now this delta y into delta z get cancelled with this delta y into delta z, as there is no variable with respect to x to differentiate. The remaining term is minus dou by dou x of k into dou t by dou x. Right? In the same way, the second term, if we consider for the second term as well, do the same procedure. First, delta y tends to 0, then the difference between the heat input and output are very small as dou qy by dou y, and substitute qy as minus k into ay into dou t by dou y. Ay is delta x into delta z. So we have finally this expression, and the limit when applied for z terms, we have limit delta z tends to 0, 1 by delta x into delta y into, the difference is very small, so dou qz by dou z. And from Fourier's law, minus k dt by dx when applied, we have this expression finally. Substitute these all expressions in this equation. We have finally this equation. No, minus into minus is plus, right? And after doing so, your all the terms having minus, and for all the simplification, when limit is applied, here it is a minus, here it is a minus, and here it is a minus. Minus to minus get plus, so the terms we have obtained are plus terms. Dou by dou x of k into dou t by dou x in x terms, dou by dou y into k into dou t by dou y in y terms, dou by dou z into k into dou t by dou z in z terms, plus a g dash. Already volumes get cancelled, is equal to rho into c into dou t by dou t. Here also the limit is applied for delta small t tends to 0, then it will be dou t by dou t. Here also volume get cancelled. Right? This is the general heat conduction equation in a Cartesian coordinates or rectangular coordinates. The equation Further simplified by dividing the entire equation with the thermal conductivity K on both sides. Then we finally no then here also one K get cancelled, K get cancelled, K get cancelled. G dash by K is equal to rho C by K into dou T by dou T. As K's get cancelled, for the first three terms, dou by dou x of dou T by dou x is dou square T by dou x square. Dou by dou y into dou T by dou y is equal to dou square T by dou y square. Dou by dou z into dou T by dou z equal to dou square T by dou z square. The final equation will be like this: dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus G dash by K equal to 1 by alpha. This 1 by alpha is came like a, here it is rho C by K, and that rho C by K can be written as reciprocating 1 by K into 1 by K by rho C, and K by rho C is indicated with alpha, coefficient of diffusion, the alpha, right? Coefficient of thermal diffusivity, alpha. So alpha equal to K by rho C. So here we got 1 by alpha into dou T by dou T. This is the final equation, the general heat conduction equation in its simplest form for a body in a Cartesian coordinates or rectangular coordinates. The equation may further be applied for some cases if there is a steady state. We are going to discuss about steady state in the later on videos. The steady state is one when the temperature change with respect to time change is equal to 0. The change in temperature with respect to time, if is equal to 0, then we say that body is in steady state. That for that steady state, the RHS term will become 0. We only left with the left hand side terms. Similarly, another case, when there is no internal heat generation, at the same time the process is not a steady state. It is a transient or unsteady state. As there is no internal heat generation, G dash will become 0. The remaining terms will be like this. Or if the body is in steady state but there is no internal heat generation, as it is steady state, at right hand side dou T by dou T will become 0 and G dash will become 0. The only terms we remain with these. So these are the important cases with the respective equation names called Poisson equation, the first case. The second case is a diffusion equation. The third case is Laplace equation, which may be helpful in solving problems of respective cases. So this is all about the derivation of general heat conduction equation in Cartesian coordinates or rectangular coordinates. Thank you.